So, for several months, I've been working on Ruins of Calica, a 3D action-adventure game made in Godot. For the enemy AI, I decided to use behavior trees because I've used them before. And so I looked around for the best behavior tree asset. I found BeeHave, which I liked, but the learning curve is pretty steep on BeeHave and in any behavior tree implementation. So it took a while to get the hang of it. And while I was learning it, I wished that I had just had an example project I could dissect. So that's what this video and the repository linked below is for. If you're like me and you want a practical example to tear down, hopefully the repository below will be helpful, and this video is an introduction to the contents of that and an introduction to the theory of behavior trees as well. The repository contains a sample level, a sample character controller, and more importantly, an actual enemy from my game for you to take a look at. I just want to say this is my interpretation of behavior trees and my understanding of how they work. There may be better ways to do some of the things that I'm doing, but hopefully this will give you a good jumping off point to discover those for yourself. Firstly, we have to go over what are behavior trees. So this is usually the behavior tree structure that you'll see posted anywhere someone is talking about how they work. You start with a root node, and then there are composite nodes that have multiple children, and then leaf nodes which have no children. Now for the rest of this, I'm going to be referring to composite nodes as branch nodes because, I don't know, I like it better. But you'll usually see them referred to as composites. So what are these nodes doing? The branch nodes are the ones making the decisions, and then the leaf nodes are the ones doing actions. For the most part, the branch nodes are never going to be interacting with your code. They're going to be interacting with other nodes. And the leaf nodes is where you're going to put all of your programming. And we'll talk a bit about that later. So there are three types of nodes that you will encounter. There's the branch nodes, the leaf nodes, and then decorators. And we're going to mostly focus on branch and leaves for this part, and we'll talk about decorators when we actually get into Godot. So branches always have multiple children, and their return value is influenced by how they process those children. And then the leaf nodes only execute code within themselves that you write to return something. But what are they returning? So every time you run one of these nodes, they're going to go through this tick function, and they're going to either return success, failure, or running. And they have these two things, an actor and a blackboard, and we'll talk about that later as well. So the leaf nodes, which is where you're going to be writing your code, there are two types. And these aren't formal types. You don't have to specify that it is one of these types, but these are the types that you're going to be using. There are conditions, and then there are actions. So conditions will check a condition and return success if true and failure if false. And action leaves will perform actions, return success if the action completes, running if the action is still in progress, and then they may return failure if the action has failed. But usually that would be under a condition leaf. These are the two basic types of branch nodes. And this is where it gets confusing, but don't worry, we're going to go over it in more detail with examples. So there are two main types, selectors and sequences. Selectors run each one of their children as long as they fail. So in this example, leaf 1 failed, so it moved on to the second leaf. Leaf 2 succeeded, so the selector succeeded. And these two never ran because it got to the success. A sequence runs its children as long as they succeed. So in this example, leaf 1 returned success, so it went on and ran leaf 2, which returned success, and then it ran leaf 3, which returned a failure, and so it returned a failure. The only way for a sequence to return a success is if all of its children succeed. And the only way for a selector to return a failure is if all of its children fail. They seem like they might be opposites or that they wouldn't be useful in their own situations. At least to me they did. But we will go over how they're useful in the example. Now, the last thing we should go over before we get into the example is how you read behavior trees. So in our example behavior tree here, which looks more like a tree, it is read left to right. So the root is going to execute this branch, and then this branch, and then this branch. But really, The root is going to execute this branch. This branch is going to execute this branch, which is going to execute this leaf. And then it's going to go back up. It's going to do this one, then this one, then this one. So it goes down from the root, and the leftmost one in this case executes all of its children, and then it goes to this one, which executes all of its children, and then it goes to this one. This is how it's going to look in Godot, and it works in a top to bottom format, going inwards into the node tree for each one. It's just a different way of representing it, but it works the same way. So this is going to be our example enemy for this, a little slime. So let's first just express this in something that might be more familiar as the state machines. We have two main states, an idle state and a hostile state. And we want to transition between them. So we want to go to hostile if you see the enemy, and to idle if you lose the enemy. Now, usually when you have a state machine, there are sub-states, or you just write the states in code. So we're just going to list out the things you're going to be doing. So in your idle state, you're going to be setting a random destination, starting to move there, and then you're going to wait until you arrive, and then you're going to start over. And you're just going to repeat that until you get moved to the hostile state. And in the hostile state, it's going to check if the enemy is in melee range, and then attack them. And if they're not in melee range, then it's going to set the enemy as the destination, start moving, and then wait. And then if you lose the enemy, then you go back to this one. So this is a basic state machine. So now we're going to work on expressing this as a behavior tree instead. So you can kind of think of these as leaves and branches. So these are leaves, these are actions that you're taking. And then these are branches. If you can hit the enemy, then you're going to do this. Otherwise, you're going to do this. But we're also missing these, if you lose the enemy, if you can see the enemy. So now, here is it represented as an actual behavior tree. And it starts at the root, and it goes to these branches, which then go to these. And you'll notice that I have these gray squares that are drawn around these two nodes, and that's because this is basically representing the conditions that you see up here. So in this case, this node is influencing this node, and we'll get into how that works. But just know that this gray box is a representation that I'm adding, and it's not part of the state machine and how it works. It's just it's just a good way of representing it. So now I've added the types of the nodes to them. And you can see these two are conditions, which is why they're in this same area, because they're influencing this sequence. So let's go into real examples that will occur. So this is our first example. This is what the slime is seeing. It's just a completely empty field. So it's going to start at the selector node. And I'm going to color nodes, the border around nodes based on what they're currently doing. And this orange means that it hasn't decided yet. It hasn't run its children yet, so it doesn't know what it's going to be returning. So the first thing it's going to do is it's going to run its first child, this idle. And the idle is a sequence. So the selector, because it's a branch, it runs its children in order. And the idle sequence is also a branch, so it's going to run its children in order and then decide what to do when it gets the return values. So the first thing it's going to do is check for an enemy. So it looks around, and there's no enemy. So in this case, we're going to say that that means that it's true, that there's no enemy, which is true. So it's going to continue. The sequence sees that the first value has returned success, and sequences continue on successes. So it's going to go on. It's going to set a random destination, which in this case is right there where the white circle is. Then it's going to go to that destination along this line, and then it's going to wait for the arrival. And this wait is blue because it's a running state and not a success or a failure. So this is going to run. Now, this is actually going to, this node is going to return running, this is going to return running, and this is going to return running. But we don't need to worry about that right now. We're going to say that it got there. So now this is a success. So this success, this is going to propagate upwards. So the first thing that's going to happen is this idle has run all of its children. They've all succeeded. So it is going to return success. And then this selector returns success on the first success that it sees. And this is a success, so it's going to return success. And when the root node returns anything, everything starts over. So now let's say this is our condition. This is our current situation for the slime. It's going to go to idle. It's going to check to see if there's an enemy. Oh, and there is an enemy. So it's going to return a failure. There is an enemy, so you shouldn't be doing this idle sequence. And this sequence is going to return a failure because sequences return a failure on the first failure. This selector node returns a success on its first success, and it hasn't seen one yet. So it's going to continue and go to the next one, which is the hostile selector. And then that one is going to go to in range, which is its first child, because it's also a selector. And now, if this is a sequence, so it's going to run its first child, and we're going to check to see if the enemy is in range of our attack, and it's not. So this is going to fail. It's going to propagate up to here, which is going to fail, and then the selector is going to go here, because it's a selector, and it returns a success on the first success, and continues on failures. The sequence is going to start here, and it's going to do this, and it's going to do this. This is all identical to the one over here for idle. And eventually that's going to succeed. It's going to propagate up, and it's going to start over. And then it's going to run through this again. It's going to find that it failed again. So it's going to go back up. It's going to go down here. It's going to go to in range. But now the enemy is in range. So this succeeded. It's going to move on. It's going to attack the enemy. This is going to succeed. This is going to succeed. This is going to succeed. So that was long. But that is a couple of frames of the game running this behavior tree. And if this is totally confusing, hopefully seeing it in action will make it make more sense. Let's just quickly go back over the two types of composite nodes after we've seen them in a practical example. So the selector continues on failures and stops on successes. You're going to want to use a selector when you only want one of its children to fully run. So if it's choosing between options, that's what you're going to want to use a selector for. A sequence is going to be done if you want a sequence of events to happen unless there is a failure somewhere in there. So in our example, if I go back, we can see that we have this sequence, which is you're going to attack the enemy, but you're not going to attack the enemy if the enemy is not in range. But this selector, the root selector, is saying you're going to either do idle or you're going to do hostile. So you're going to try to do idle, and that's going to fail, and then you're going to move on to hostile and check that. And then let's also go back to the tick function that I talked about earlier. So there were these two parameters in the tick function, actor and blackboard. So the actor is the Godot node that this is going to be influencing. And we'll get into that when we get into Godot. But when I say node in this case, I'm referring to a node in the Godot scene tree. So when you're writing code inside of the tick function, the actor is the thing you're going to be manipulating outside of the tree. So that's the function that's going to make it walk somewhere or change it to attack or whatever else. The blackboard, I will admit I've never actually used it, but it is where you can store variables that can be accessed by multiple behavior tree nodes. So this is a sample function that we can look at. So in this, we have our tick, we have our actor, and then this is just checking to see if a cooldown is done. So there's two types of cooldown. Let's just worry about this first one, this in cooldown. So it's checking if the actor, which is an agent in this case, is in a cooldown, which is a variable built into that script. And if it's true, then it's going to return failure. And if it's false, then it's going to return success. So this would be run before the enemy attacks, for instance, to check if the attack is in cooldown. Because if it is in cooldown, this is going to return a failure, and the rest of the sequence is not going to run. So next, we're going to go into Godot itself and go over this in the actual context. And in fact, we're going to be looking at basically this exact same tree, but in Godot itself, seeing how it works. So here we are in Godot, in this sample scene with our enemy and our player. So why don't I just go ahead and play it for now, and we can just see. So I can walk around. I have turned on the debug for the navigation agent, so you can see that. So it was in idle state, now it's starting to follow me around, but if I go far enough away, maybe it'll lose me and go back to idle. There we go. So now it's just back to wandering around. But if I get too close to it again, it'll start following me again. If I get way too close, it'll start attacking me. So how does this all work? So the way BeeHave works is you write a bunch of scripts. These scripts are attached to the leaf nodes. So here I have action leaf, and then some of them are condition leaf. So if I look at this one will make the enemy face, or the actor face its enemy, and if it is facing it close enough, it will return success. Otherwise, it will return running. So this is ran whenever the enemy or whenever the agent is close to its enemy, but it's not facing them. So in this case, this hitbox that you can see here, if this agent's enemy is not in that hitbox, it will rotate until it is. So that's an example of the kind of scripts that you'd be writing. But let's just take a look inside of the tree itself now. So this is the entire thing. It works very similar to the one that I talked about in the presentation. I'm not going to go over the step by step again, like I did in that presentation, because you can actually go over it yourself. So this is one of the cool features of BeeHave. If I just open this up and I can push it over here, I go to the debugger, then I go to BeeHave, and then I click on this. So now I have this, the actual tree. So I can just open this all the way up. You can press this button to flip which way it is. I don't know which way would be better. Let's just do it this way. As much of the screen as we can. So currently you can see it is executing its idle. It is waiting until it gets to the destination, and then it's waiting for a couple more seconds, setting a new destination, waiting until it gets there. But if I go here, now it's executing all of these things, and now it's executing that, and you can see exactly what it's running and how it works. So that's very, very nice. So now that we've seen in action, let's take a look at what all of these nodes are doing. So if I go to add node and then I go inside BeeHave node, we have our leaves, which are again all going to be programmed by you. So we'll skip those for now. And then we have our decorators and we have our composites. The composites we went over before in the presentation. You have your selectors, you have your sequences. We have these sequence star, sequence reactive, selector reactive, and then some randomized ones. These are explained in detail in the docs. And then in the decorators, we have a bunch of different types of decorators. These all do special things. They have one child and they modify the return value of that child. So for instance, this always succeed decorator here, make sure that this entire thing will only ever return success. So it runs it, and then this selector will return either success or failure, and this always succeed will return success no matter what. And all of these have their own special functions, and you can look into them again in the docs. This behavior tree is going to be the brain of whatever you are attaching it to. In this case, I have this agent, and this agent is handling how it moves. So it's a rigid body, and the agent's job is to send information to the navigation agent and to these raycast and to ground check, attack box, damageable, all of these things. And it receives its instructions on what to do from the behavior tree. If I turn off the behavior tree, like so, the slime will no longer do anything, because the behavior tree is how it thinks. Something else included in the repository that you may find helpful is I go into the file system and I go under objects, and BeeHave trees, I've included several other behavior trees from other enemies in my game. I can't include the actual enemies because I do not have the rights to distribute the models and the sounds, but I've included the trees anyway so that you can look at them, see how they work, shake your head at the badly written code, whatever you'd like. I don't care. You can do whatever you want with them. Thanks for sticking around all the way to the end of this video. Didn't imagine that it would be this long when I started working on it, but there was a lot to go over. The link to the repository, again, is in the description, as well as a link to my game if you would like to play it and maybe compare the behavior trees that you can see in the repository to how they're working in game. I also have a link to some other resources down there that you may find helpful going over behavior trees. There's one specifically about BeeHave down there that I found helpful while researching how to make this. And good luck with your projects. If you have any questions, let me know down in the comments. Thanks.